Okay, let's start with number 7. With these simple ones, we can just kind of point at certain pieces of this integral and say this could be u, and if that were u, then this would be the derivative of u. And now we can rewrite this as u to the 4th power times du. And this looks exactly like x to the 4th dx, right? It's pretty simple. It's just a power function. And to take the antiderivative of that, we would make sure to add 1 to the power and then multiply by 1 over that power, so that when we multiply 5 by this, 5 times 1/5, we get 1. When we subtract 1 from the power, we get 4. And we'll throw a plus c on there. But then we have to just replace what u actually represents. It actually is representing 1 plus 2x, that's raised to the 5th power now, plus c. And if we were to take the derivative of this, which would be the way we would check our answer, then 5 times 1/5 would be 1 right there. Subtract 1 from the power, that'd be 4, of 1 plus 2x, right? And then the chain rule says we'd multiply by the derivative of the inside. Multiply by the derivative of the inside, that's 2 dx. So that's our check to make sure that we have done the work correctly. Let's do number 11. And that says the integral of x to the 3rd times x to the 4th plus 3 squared dx. Alright, so I'm just going to show you what my choice of u would be, and as we do more and more of these, I think my choice of u will be more and more apparent. So I'm going to say that this is u, okay, this thing inside the squared function. Now, if I were to, let's write u over here. U is x to the 4th plus 3. If I were to take the derivative of u, it'd be nice if it worked out like this, where this times this is du. And it's really close, but the derivative of this would be 4x to the 3rd dx. But we don't have a 4x to the 3rd. Though we could put a 4 right there, and now we have 4x to the 3rd dx. That would be du. So can we do that? That's the question. Can we just put a 4 there? Well, yes and no. We can put it there, but not just a 4, because what we started out with, remember, was all this green stuff. It didn't have a 4 there. So we have to counteract that. Okay, so you see, when we multiply by 4, we're multiplying this whole thing by 4. It's just 4 times x to the 3rd times this times dx. So if we were to multiply the whole thing by 1/4, that would be like we didn't do anything. 4 times a 4th would just be 1, and now we're back to the same thing. So if we were to put a 1/4 there, well, we could just take out that constant multiple of 1/4 and put it out here. So now what we have is u, and then du is 4x to the 3rd dx, just like this says. So this with this is du. So now this becomes the integral of, okay, this is u, and it's squared, u squared, times the rest of it is du. So this becomes 1/3 u to the 3rd plus c. Should be pretty good at that by now. We add 1 to the power, we put a coefficient out here such that when we multiply by this 3, we get 1. Okay, but we also have this 1/4 on the outside that we had multiplied by to fix this to be du. Okay, so now we have 1/4 times 1/3 times u to the 3rd plus c. So what we have here is 1 over 12 times u, which is x to the 4th plus 3, okay, and that's to the 3rd, plus c. Okay, so, and then we could take a few moments and check this, and we multiply by 3, and we get 1/4 x to the 4th plus 3, and then we'd multiply by the derivative of the inside. That'd be 4x to the 3rd, so we'd get that 4x to the 3rd, and now that would be 1/4, and 1/4 times 4 would cancel everything out, and we'd be left with x to the 4th plus 3 to the 2nd times x to the 3rd dx, just like we want to. Okay, number 16. Alright, so I hope this time that I do this problem, you start to see why I choose u the way I do. I choose u so that somewhere else in the integral, I am going to see the derivative of this, and I do, or at least it has the right power, and then I can fix it the way I did here. If this is u, well, let's write that over here again so we can keep track of everything. U is t to the 4th plus 5, and if that's u, then the derivative of u would be 4t to the 3rd plus c. Well, not plus c, sorry, this would be d. dt. So I want 4t to the 3rd dt in order to replace it with du, but it's not quite right. It's just t to the 3rd dt, but I could again put a 4 there and balance that out with a 1/4, and so now we have 1/4 times the integral of, well, the square root of u, and then 4t to the 3rd times dt is altogether replaceable by du. And we could write this as 1/4 times the integral of u to the 1/2 power du. Okay, then we have 1/4 times the antiderivative of u to the 1/2. Well, I'd add 1 to this power, that'd be 3/2, u to the 3/2. And then we'll put a 2/3 here so that when we multiply by 3/2, we come out with 1. Okay, and this 1/4 comes from right here. And then we add c. Okay, then we go back into terms of t, right? We replace u first, or what u was to begin with. So u, this u right here, is t to the 4th plus 5. So we have 1/4 times 2/3. That's going to be, 2 is going to cancel with a 4, so it's going to be 1/6. 1/6 times u to the 3/2. U is t to the 4th plus 5. I'm going to raise that to the 3/2 and add c. That's it. And again, if we were to take the derivative of this using the chain rule, this is what we would wind up getting. Alright. We'll move on to 20. Integral of x to the 3rd over, so this one looks different. This is a fraction, so we're going to figure out what can we do with this. Okay, so if I just, if I kind of follow the rule that I just suggested and say that u should be such that somewhere else I see the derivative of u, or something very close to it. So if I choose this to be u, the derivative would be an x to the 3rd. Okay, it would be 4x to the 3rd, but we can work with that. So we'll call this part u, and so that would make, well, let's see what would happen. If that was u, then we'd have 1 plus x to the 4th is u, and the derivative of that would be, well, 0 plus 4x to the 3rd dx. So we need a 4x to the 3rd dx. Okay, so that's du. This is u. This is du. Okay, so we see we've got some cleaning up to do for sure. Now we have the indefinite integral of, let's see, du over u squared. We could write this as the integral of u to the negative 2 times du, because this would be 1 over u squared, and we could multiply that by du, and that's what we would get. Okay. Oh, we forgot something here. We multiplied by 4, so we also need to balance that out with multiplying by 1/4. Okay. So this is 1/4 out here, 1/4. Okay, so this, the antiderivative of this would be 1/4 times. We're going to add 1 to the power. Add 1 to this power, you get -1. That trips people up a lot. They want to make it -3, but remember we're in the negative numbers, so if we add 1 to -2, we get -1. And so if I want to take the antiderivative of this, I would want to have a positive 1 come out, but right now I'd have a -1, so I'll just put a negative there. So 1/4 times negative u to the -1 plus c. So that does it for us. We're going to now go back into terms of x, and so we have 1/4 times, let's say -1/4, and 1/4 times negative. So -1/4 times u, which is 1 plus x to the 4th. Let's see, 1 plus x to the 4th to the -1 plus c. And if we wanted to, we could write this in the denominator and have -1 over 4 times 1 plus x to the 4th plus c. If we wanted to, we could do -1 over 4 plus 4x to the 4th. Distribute that 4. It doesn't really matter. Plus c. Okay. So this should start to get our thought process rolling along. We choose u to be a function so that the rest of the function that we're multiplying by will be do u, so that we'll get something of the kind u to the n times the derivative of u, which we could treat like x to the 4th dx, or x to the 1/2 dx, or x squared dx, and so on. So you can see how most of the time we're going to wind up getting, like I said before, we're going to wind up replacing something with u and getting something like u to the n du, and getting u to the n plus 1 times 1 over n plus 1 plus c. That happened all 4 times here. It'll keep happening for a lot of these. So let's see some more. After 20, let's do 26. The indefinite integral of x squared plus 1 over 3x squared dx. Here is a difficult one, in a sense that now you're all geared up to take or to look for u and du, but we don't want to get so caught up in that we don't recognize just old kinds of derivatives. You know, this is just a power function plus another power function. We don't even need u substitution. We could just write it like this. This is x squared. This would be 1 over 9x squared if we squared both of these, 9 and x squared. So that would be, let's see, 1/9, right? 1/9 times x to the -2. Okay, dx. So I can take the antiderivative of this, add them together, right? So this would be 1/3 x to the 3rd plus, okay, so if I add 1 to this, it'll be x to the -1. And if I want to wind up with a positive 1/9, so this -1 is going to come down and multiply by something, and we're going to wind up with a positive 1/9. So this should be a -1/9. Right? If I put a -1/9 there, the -1 times -1/9 would be positive 1/9. Subtract 1 from the power, get -2. Right? Didn't need u substitution there. That's the hard thing. When you learn a new skill, you get good at it, and you're rolling along, and then you can't see how to apply it, and it turns out you don't need it. It's old. You don't need that old kind of or you don't need that new kind of tactic. You go back to the old ones. So that's the tricky one. It gets all mixed together. When do I use this new thing, and when do I use the old thing? And it takes some skill and practice, and there's just no substitute for it. 33. This one here it kind of feels like this might be u, and then this might be du, but this is not the derivative of u. The derivative of this would be just like negative dy. That's all it would be. It'd be 0 minus dy. So, that's not working, and what do I do? Well, there's no power here, so there's nothing stopping you from combining these. So we could get 9 times the square root of y minus y. Let's say y times y to the 1/2. When we distribute this y, that could be y to the 1/2. And then the whole thing's times dy. So this becomes the integral of, let's say, 9y to the 1/2 minus y to the 3/2 dy. And now we take the derivative like normal. We add 1 to the power. That's going to be y to the 3/2 for this one. And what are we going to multiply 3/2 by to get 9? Let's see. 3/2. So if we do, 6? Yeah, 6. And so that question, it's not a very hard question. We're gonna bring down this 3/2, and we're gonna multiply it by something, right? Like x, or just something, and we want to wind up getting 9, right? We're gonna 3/2 times something should give us 9, and so we'll multiply by 2/3 on both sides. So x equals, divide that by 3. That's 3 times 2 is 6. So I made it look a lot harder than it should have looked. Minus, okay, so y to the 5/2. This one's easier. This will just be 2/5. Okay, and plus c. And if we took the derivative of each of these, we would get that, and then we could write it like this, and we could factor out the square root of y. They just wrote it in a tricky-looking way to get you to try and choose this for u, and then get confused when this wasn't du. And it worked on me plenty of times when I was studying calculus, so that happens. All right, 44. Now we're going to just throw some trig functions into the mix. As I explained in the intro video, you're just going to, most of the time, do the u to the n, right? It's going to be like these up here. It's going to be some function to some power, and then you take the derivative by adding 1 to the power and multiplying by the reciprocal of that power. But here we actually do see some trig functions. So now we want to start thinking, maybe my integral is going to involve like the cosine or the sine or the tangent or something. So something to think about. So if we let this be u, then the derivative of u, let's look at that. U is x to the 4th. So du is 4x to the 3rd dx. And that's what we have, 4x to the 3rd dx. This with this is du. So what we could write now is the antiderivative of the sine of u, right? Sine of u. The rest of this is du, so just du. And what's the antiderivative of the sine of u? It's the negative cosine of u plus c. And so this goes back in terms of x as negative cosine of x to the 4th plus c. That's our antiderivative. Let's do another one. Do 50. Okay, antiderivative of secant of 1 minus x, and the tangent of 1 minus x dx. Alright, so now secant times tangent, if we let u be equal to 1 minus x, these both have the same thing, so u equals 1 minus x, the derivative of u would be negative dx. Okay, so we have dx, but we don't have negative dx. So if we put a, if we said multiplied by negative dx, that would fix it. But we'd have to put a negative out here to fix that. So now we have negative integral of secant u tangent u du. And this is the derivative of the secant. So we have negative, right? Negative secant u plus c, and u, let's go back in terms of x now. U is 1 minus x, so negative secant of 1 minus x plus c. And that does it. Now let me show you an example where that doesn't necessarily happen. Let's jump back to 49. That's going to be the integral of sine 2x cosine 2x dx. If I let u be 2x, like I normally kind of would, it's like this function that's inside the function is kind of what it turned out to be so far. Well, if u equals 2x, then du equals 2 dx. And then I'd have to put a 2 here, and then all I really wind up getting is sine cosine du, essentially, with a 1/2 out here. And I don't know anything that has a derivative of sine times cosine, so now I've confused myself. So that didn't work. I don't know anything that has a derivative of sine times cosine. But if I let u be sine, this is u, the derivative of sine of 2x is cosine of 2x, and a little bit more. If u is sine of 2x, then du is equal to the derivative of sine is cosine, 2x. The chain rule says now I multiply by 2, times the derivative of the inside function, right there, so that'd be 2 dx. So now this becomes, if I put a 2 here, so 2 times the cosine of 2x times dx, that much would be du. And then I'll put a 1/2 there to balance that out. So now this becomes 1/2 times the integral of u times du. So it turns out it doesn't involve trig functions at all in this expression. Not like it did in the previous one, in number 50. So now we have 1/2 u, let's see, let me go back, 1/2 times 1/2 u to the 2 plus c. So now when I replace u, I get 1/2, I should do 1/2 times 1/2 is 1/4, so 1/4 u squared, u was sine of 2x, so sine squared 2x plus c. Okay, so it turns out I don't even have a sine function here. It turns out this was of the form u du. Okay, so even, or just because there's trig functions there doesn't mean that you're just going to let u be the inside of the trig function. And let's give 60 a try. They're giving us the information that there's a function that has this derivative. There's some function f, and its derivative is this. And they want us to find the function that has that derivative, and not only does it have this derivative, it specifically goes through a point. And I think I'll save that and tell you why that's significant here in a second. So first, if we want a function that has this derivative, we're talking about the antiderivative. So the antiderivative of the secant squared of 2x dx. So this is involves a trig function. So if we wanted to strictly use u substitution, we could let this be u. This is 2x. So, should be u. So u is 2x. Du would be 2dx. So we need to put a 2 there with the dx, so that this is du now. So this is now the secant squared of u du. The secant squared is the derivative of the tangent. When we put the 2 here, we should have put a 1/2. We've done that enough times. So now we have the secant squared of u du, and that's the derivative of the tangent of u, with a 1/2 there. Okay, and then we'll put it back in terms of x. This is 1/2 tangent of 2x. And it's that plus c that now makes that point that I mentioned earlier. It makes it significant now. This plus c, any number of functions, and there's an infinite number of functions that have this derivative. Just make c different, and then when you take the derivative of c, a constant, you get 0. So this could be 5 or 70 or negative a million. It doesn't matter. All those functions will still have a derivative of secant squared 2x. So to find out what that c is, we're given this information, that this function goes through pi over 2, comma 2. So what that means is if we plug this in for x, we get this out for y. This is f of x. And so if we plug in pi over 2, we should get out 2. So f of pi over 2 is 1/2 tangent of 2 times pi over 2 plus c, and that should give us 2. So we have c is equal to 2 minus, I'm just going to subtract this on both sides, 1/2 times, well, what's the tangent of, this would be, the 2's would cancel, would be pi. The tangent of pi is 0. So c is 2. So now we can rewrite this and say, now we know that c is 2. So the specific solution, or the specific function that has this point on it, is 1/2 tangent 2x plus 2. Because now we found what c is worth. Now let's go for number 64. Makes reference to this example 5. So let me show you what happens when we do a typical choice for u by letting u be the thing inside of another function. If we let u be 2x plus 1, then du is 2dx. And if this was the number 2, then we would have 2dx, and everything would work out just great. But that's not the way it is. In fact, we have a first degree polynomial here and a first degree out here, and so it doesn't seem to help us much to let this be u. But the trick they use in example 5 is to still let u be the thing inside the square root. So let me show you kind of what happens there. We get this square root of u. Now that part is a little simpler. When it comes to take the antiderivative of the square root of u, we can write that as u to the 1/2, and so that becomes easier. But then what we can do after that is to solve for x in terms of u, and then the thing outside of the square root becomes the thing that's a little more complicated, but then it's really manageable after that. So let's bring this down here and say that x, well, we'll solve for x. So 2x will equal u minus 1, and then x will equal 1/2 u minus 1. So we could put a 1/2 here, put a u minus 1 here. All right. And du equals 2 dx. So we could put a 2 right here. We have this 2 dx. That would be du. Okay. But then we'll have to put a 1/2 out here. So that's another 1/2. And then we get to write that as du. So here we have 1/4 times this integral. Well, if we write this as u, instead of square root of u, we write it as u to the 1/2. We can distribute this u to the 1/2 to each of these things, and we get u to the 3/2 minus u to the 1/2 times du. And now this integral becomes much easier to find. So we have 1/4 times u to the 5/2, and we'll put a 2/5 out here, and minus, and we'll have u to the 3/2, and we'll put 2/3 here, so that if we were to take the derivative, we would wind up with 1 times u to the 1/2, and plus c. So I think your typical answer is your final answer is going to look like this. Each of these has, let's see, they have a 2 in common, so you could factor out that 2. They also have a u to the 3/2 in common, and that would look like, when you factor that out of here, you'll have u and 1/5 u. 1/5 u minus 1/3 u. Well, no u, we factored that out. So all in all, this could be written as 1/2 u to the 3/2 times 1/5 u minus 1/3. You might think it's simpler to distribute the 1/4 and just to have that given to each of these terms. Usually the answers in the back of the book will go for factoring something out that's in common. So that's most likely the answer that you'll see in the back of the book. Alright, so now let's move on to, and now we'll move on to number 71. This is the definite integral from -1 to 1, x times x squared plus 1 taken to the third. So this is not a very complicated integral to find. It's just stepping into the definite integral territory. So first we need to find the antiderivative. And once we find the antiderivative, we'll plug in 1 and we'll plug in -1 and subtract, like the fundamental theorem of calculus says we can. So we will let u be x squared plus 1. So u is x squared plus 1. Du is 2x dx. And now we need a 2 to be there so that we can have 2x dx. We'll put a 1/2 in front. And now we can make this 1/2 times the integral of u to the third du. And we have 1/2 times 1/4 u to the fourth plus c. And in terms of x, that would be 1/2 times 1/4 times x squared plus 1 to the fourth plus c. And just make that a little easier, we'll do 1/8 times x squared plus 1 to the fourth plus c. Now we use the fundamental theorem of calculus, and we plug in 1 and then plug in -1 and subtract. So that's 1/8 times 1 squared plus 1 to the fourth minus 1/8. I don't know why I want to put half so badly. Times -1 to the second power plus 1 quantity to the fourth. So now what we have is 1 plus 1 to the fourth. That's 2 to the fourth. That's 32 divided by 8. That's 4. Minus, the same thing happens here. 1 plus 1, that's 2 to the fourth is 32. Times 1/8 is 4. and we get 0. Always is nice to do all that work and get 0 or 1 as our answer. That will happen though. Now we'll do 77. The computer's kind of freaking out. That's the definite integral from 1 to 9. Square root of x times 1 plus the square root of x and squared dx. Alright, so we have to find the antiderivative of this first, and then we use the fundamental theorem of calculus. So just do 1 over square root of x times 1 plus root x squared. Alright, so what do we let be u, and what do we let hope for du to be? I'm going to follow my instincts here, and I see this is inside of the square function. Let's see where this leads us. This will give us 0 plus 1/2 u to the negative 1/2. Let's see. No, I just took the derivative in my mind. U is 1 plus the square root of x. And du is going to be 0 plus 1/2 x to the negative 1/2. See, all I did was let x, square root of x, be x to the 1/2 and take the derivative there. So, now if we rewrite this as 1/2 times 1 over the square root of x, and we also rewrite this as 1 over 1 plus the square root of x squared times 1 over the square root of x dx, we see that we have 1 over the square root of x dx right there. We just need a 1/2 multiplier, and here is du. This here is 1 over u squared, so we could write this as u to the negative 2, and we wouldn't have any problem. So now that we put that 1/2 there, we'll put a multiplier of 2 outside to balance that out, and we can write this as 2 times the antiderivative of u to the negative 2 du. Okay, so it takes a little bit of practice and skill to see this for what it could be, and to rewrite it this way, or just to see it this way, and to see that this thing that's down here actually could be pulled over here with the dx and be part of the derivative of u. And now that we have 2 times u to the negative 2 du, we have 2, and the antiderivative would be negative 1, just negative 1 really, just negative u to the negative 1, and plus c. So, now putting it back in terms of x, we have 2, and this should have been multiplied, so negative 2 times u, which is 1 plus root x, to the negative 1, plus c. And now we'll use the fundamental theorem of calculus and plug in 9 and plug in 1 and subtract. So we have negative 2 times 1 plus the square root of 9 to the negative 1 minus a negative 2 times 1 plus the square root of 1 to the negative 1. So here we have negative 2 over, see this is basically in the denominator, 1 plus 3, that's a 4, plus 2 over 2, so we have, let's see, 1/2, negative 1/2, plus 2 halves, for a total of 1/2, a positive 1/2. So just as we do more u substitution, we can do a little more, trickier and trickier substitutions to find more difficult antiderivatives. So a good tip to start, like I said, a lot of times it's some trial and error, just guess and see what works. Try letting u be the thing inside of the square, being the thing inside of the sine, of the cosine, inside of the third root, or things like that. And just take u down, and write it down, take the derivative of u, and see if you can work with what's left in the integral. In general, that's all I do, and I've just gotten better at looking and seeing what it's going to be in my head before I do it. 88. That is a problem where they want us to find the area under a curve, which they plainly show us is the definite integral from the left side to the right side of the function x squared times the third root of x plus 2 dx. So if we follow what I hope would be our instincts at this point to let the inside of the cubed root be u, then u is x plus 2, and the derivative is, the derivative of u is dx, which is good news. But it's not x squared dx. That's what we would need. We need x squared dx. So that didn't work out. But we notice that we could take this and use it to write x in terms of u. We just subtract 2 from both sides. We get u minus 2 is equal to x. So this turns into that like example 5 thing, like 64 said, use example 5 to do these problems. So this is du, and this becomes u minus 2, and we'll square that. So let's rewrite it as u minus 2 squared times the third root of u du. And you might be asking yourself, how in the world would I even know that I want to do that? For one thing, it turns the thing inside the cubed root into a single variable, right? We replace it with just u. And here, the thing that's being squared is a little more complicated, but we can square things. We can square binomials, trinomials, whatever we want. But we can't handle third roots or square roots of something more complex like that. But if you think a few steps down the road here, we can square this out. We can write this as u to the 1/3, and we can distribute it into there, and now all of the things will just be, with a funky power of u. But still, if we get it as u to a power, which I told you, like 95% of the time, that's what we're going for, we can finally take the antiderivative. So if we just start by squaring this, which will give us u squared minus 4u plus 4, and then we'll do it times u to the 1/3 power, and du. Now you can distribute this 1/3 power, this u to the 1/3 power, and get u to the, this would be 6/3, so times u to the 1/3 would be 7/3, minus 4 times u to the 4/3, plus 4 times u to the 1/3 times du. Now we take the antiderivative. We just add 1 to the power and multiply by the reciprocal of that new power. So this would be u to the 10/3. And since when we take the derivative, we would multiply by 10/3 out here, and we don't want 10/3, we want 1. We put the reciprocal, and takes care of that whole thing, just cancels that out. Okay, now, minus 4 times, now we do it to this one, u to the, let's see, 7/3, and then we do 3/7 here, to cancel it out when we would go to take the derivative, plus 4 times, we have u to the 4/3, and we'll multiply by 3/4, and we get our plus c there. Ooh, that's quite a thing. Now let's do a couple things. Let's put back in terms of x instead of u, and at the same time, like we'll multiply these fractions together. So we have 3/10 times x plus 2 to the 10/3 minus, this will be 12/7 times x plus 2 to the 7/3 plus 4 times 3/4 would actually just come out to be 3. U to the 4, oh sorry, not u. We just said we were going to replace u with x plus 2 to the 4/3 and plus c. Now, it's our job to plug in 6, then plug in -2 by the fundamental theorem of calculus, and subtract. So we'll do the 6 in orange and the -2 in white. So here we go. 3/10 times, what do we code in here? 6 plus 2. 6 plus 2 is 8. Okay, so we put the 6 in there, and that becomes 8. 8 to the 10/3 minus 12/7 times, again, 6 plus 2 would be 8 to the 7/3 plus 3 times, again, 8 to the 4/3. Alright, so that is the 6 part, and now we will do the second part of the fundamental theorem, and that's to subtract when we plug in the lower limit a. So again, we have 3/10 times -2 plus 2. -2 plus 2 would be 0, and raise that to the 10/3. Well, 0 to the 10/3 would be 0 times 3/10 would still be 0, and that's just going to keep happening. We're going to subtract, you put 0, raise it to a power, that's 0, times a number, that's 0. So minus 0, let's check, yeah, 0 raised to a power times a number, still 0. So this accounts for nothing, there's nothing there. So what we have left is, well, this 3 in the denominator of the power is just the same thing as the third root. And then we take the third root of this number, and we raise it to the 10th power. We could raise it to the 10th power and take the third root, whatever we want. But taking the root first makes it smaller, and then we can raise it to the power. So we'll have 3/10 times the third root of 8. That's 2. And that'll be raised to the 10th power, minus 12/7 times third root of 8 would be 2 to the 7 plus 3 times 2 to the 4th. Okay, and this at this point, we could write this as 1024, 128, and 16, but to get any idea of what it all adds up to, we get our calculators out. So we get our calculators out. We multiply it all together, add everything, and we get 135.771, let's say. So that would be the area under that curve, given that that curve is all positive and above the x-axis. So it did take a little bit of tricky thinking, but it's just one of the more things, one more of the things that we can think of to do when we have an antiderivative and we do use substitution and it seems like it doesn't help at all. We can try and take this fairly simple expression with just an x, rewrite x in terms of u, make that substitution. We can square that out. Even if this was a cube, we could cube it out, and whatever it took, we could multiply it out and then write this as u to the 1/3 and distribute it in. And it gets a little funky looking, but it's definitely doable. So there you go. I hope that was helpful. Comment or contact me if you have any issues. Thanks for watching.